I have got to confess two things. Okay. First of all, I am no expert on slabs on ground. I am also no expert on cracking in concrete. So design of GFRP reinforcement for crack control in slabs on ground. What in the world is she doing here today is probably what you're asking. And I kind of wondered myself too. But what I want to try to do is maybe provide some food for thought, some ways to think about what we have, what we know about use of GFRP reinforcement, and I will admit having some knowledge in that subject, and how can we take what we know about GFRP reinforcement and apply it for crack control in slabs on ground. Not a whole lot of there are examples out there. There hasn't been a lot of definitive work done to quantify what we're seeing, though that is starting to change. And I think that maybe you had a speaker this morning who addressed that a little bit. Let's see if I can get this to work. Which way does this go? Am I holding it wrong? Hold on. Oh, that's the pointer. You know what? It'll be easier for me to just work from here. Which one? That one. That's counterintuitive for somebody who's left-handed. Okay. So the first thing I'll say is, not being an expert on slab on ground, where did I go to the experts? And the expert knowledge is in 360, the ACI Guide to Design of Slabs on Ground. And I am going to be fairly narrowly focused here. I am looking at material related to unreinforced slabs, where we want the cracking to occur beneath the saw-cut contraction joints, or where we're maybe lightly reinforcing, and by lightly, 360 says maybe 0.1% steel across the joints to enhance the aggregate interlock for load transfer effectiveness. And then I'm also going to look at those slabs that they categorize as being reinforced for control of crack widths. And those slabs are designed to remain uncracked under the design loads. The guide recommends reinforcement maybe in the neighborhood of 0.15% steel with closely spaced contraction joints, but they don't want the reinforcement to be continued through the joints because that can tend to, especially with steel, with its high stiffness, can lead to cracking in other locations of the slab. And right there I point to where maybe we have one advantage with using the GFRP reinforcement, because we're not going to provide that same stiff resistance. I'm also going to look at what they call continuously reinforced slab, where PRC 360 suggests 0.5 to 0.7% steel, okay? This would be slabs on ground where you're not requiring contraction joints, and you provide the reinforcement to form narrow, closely spaced cracks. So that's kind of where my focus is today, where you see those two blue arrows. And I wanted to take a look at what guidance we have from our code, 440.11, and from the 440.1 guide on use of FRP reinforcement to come up with maybe a suggested approach for how we can address control of cracking in these slabs on ground. A couple things here. Looking in what PRC says, I think it's important to note that the guide makes clear, the 360 guide makes clear that properly placed reinforcement, even when it's used in suitable amounts, is not going to eliminate cracks, okay? The idea is to reduce crack widths to what are acceptable levels, and the 360 also makes clear that joint spacing, slab thickness, And the reinforcement requirements fall on the designer. Those are the designer's responsibility. To aid the designer, they provide now in the 360 guide the little chart I have shown here that indicates that depending upon what your slab thickness in inches would be, and that would be chosen based on your design loads to make sure that you don't crack your slab under those loads. Once you've done that, one can figure out then, depending upon the type of concrete you're using, slab thickness, about what space do you need for your joints. Used to be they provided a rule of thumb that said, hey, joints should be spaced in feet, about 2 to 3 times the slab thickness in inches. Some other guidance from the 360 guide. Note that if we're talking about reinforcing for crack control, that reinforcement should be placed in the top of the slab. In fact, I think they say upper third of the slab. The use of bottom reinforcement may actually increase the cracking that we see because it's going to create additional restraint in the bottom of the slab. They also note that your load transfer effectiveness by aggregate interlock, okay, it's going to be inversely proportional to the width of the joint opening and the load magnitude, but directly proportional to slab thickness and going to depend upon square root of the subgrade modulus. The suggestion in the 360 guide is that if your joints are limited to about 25 to 35 thousandths of an inch, 0.6 to 0.9 millimeter, if that's the biggest your joint openings are, you should be able to efficiently and effectively transfer your load by aggregate interlock under most conditions. A caveat to avoid continuing larger percentages of reinforcement across contraction joints. Example of this would be using the 318.18% temperature and shrinkage steel requirement. If you continue that through your joints, you may experience random out-of-joint cracking because that reinforcement coming through the joint is going to restrain your joints from opening, and the cracks are going to form, but they're going to end up forming maybe somewhere where you don't want them to form. All right, some other recommendations that we get out of 360. I would point to the fact that, and I found it interesting, trying to decide on, and jumping ahead a little bit, the 440.1 guide for use of FRP reinforcement has an appendix for slabs on ground. And that appendix makes use of this, the traditional subgrade drag formula, SGDF, but I find that it no longer shows up in the 360 guide recommendations. The explanation I was given for that is because it may result in steel percentages that aren't able to restrain crack widening enough to promote the load transfer we need. But yet, when I look at the design examples that are in 360, all the design examples are based on that subgrade design formula. So go figure, I don't have the answer to that one. Where I get my information, by and large, comes from these documents, the 440.11 building code requirements for structural concrete, and the 440.1 guide for the design and construction of structural concrete. The first one, the code, is limited to GFRP bars solely. The second, the guide, covers other types of FRP bars as well. And the guide includes additional background in an appendix with recommendations for using FRP reinforcement in slab on ground. That guide is currently in the process of being updated. I cannot tell you what's going to happen to that appendix when that update is completed, whether it remains, changes, or goes completely away. The other thing I point to briefly is that the nice thing is that ACI code 440.11 is now in the International Building Code in the 2024 version of it. But please note that 440.11 is very specific that it does not cover slabs on ground. And we see that there in the 1.4.8 provision. This code does not apply to design and construction of slabs on ground unless the slab transmits vertical loads from other portions of the structure to the soil. So it's not part of the building code requirements, but that doesn't necessarily mean we can't borrow things from it to address maybe what we're trying to achieve with slabs on ground. And in fact, if we take a look in the commentary, 440.11 points you to the ACI 360 guideline or guide for slabs on ground that can then be used in conjunction with the guidelines found in 440.1 for those designs. So what information can I get out of the code and the guide? And I'm first of all going to go look at that shrinkage and temperature reinforcement, okay? Because when we apply it in beams, one-way slabs, structural slabs, we're using it with the intention of limiting our crack width. The reinforcement ratio we use is right here, down here in equation, that's equation 24 in 24.4.3.2. There's the reinforcement ratio with GFRP reinforcement. If I'm using the lower modulus bars with an EF out of 7957 of about 6,500 KSI, I'm going to get a reinforcement ratio of about 0.003 from that. If I'm using higher modulus bars, that's probably more like about 0.0023. Okay, to give you some context for how big that ratio is. And we do apply it to the gross concrete area, as is done with the steel reinforcement ratio for temperature and shrinkage resistance. Here, though, bar spacing is limited to the lesser of 3 times the slab thickness than 12 inches. Where did we come up with that ratio from? It is intended to provide the same force capacity as the 0.0018 ratio from 318 provides with grade 60 steel. But keep in mind, we're providing the same force capacity, we're providing that at a smaller stiffness, right? Okay. And the other thing I can tell you is that that reinforcement ratio will correspond to about a 0.028 inch estimated crack width, about 0.7 millimeter estimated crack width at surface load levels, to put that into some context. The question that we need to answer, and I don't know that it's been totally answered yet, is will GFRP reinforcement in this amount create the probability of random out-of-joint cracking like using steel, when you put it through the joints, the way steel reinforcement at 0.18% will do, okay? No definitive answer yet, but certainly from the couple of studies I've seen, there certainly is the possibility that the answer to that will be no. We're going to get the cracking where we want the cracking, which is in the joint. Other equation we can get from code 440.11 that will be helpful to us is how do we space our GFRP bars for crack control. And if we take a look, these equations here, 2432A and 2432B, come right out of code 440.11. They have been calibrated to provide a 0.028 inch or 0.7, actually I guess it's 0.71 millimeter maximum crack width. Now those coefficients, the 0.032 and the 0.026, can be linearly adjusted to impose a more restrictive limit if the designer felt it was necessary. The 0.032 actually comes from 1.15 times the maximum crack width you want to accept in inches, and the 0.026 is from 0.92W. So this equation could be adjusted I don't think I would adjust it higher. I don't think I'd make my crack width bigger than that 0.028 inches, because remember, we want to maintain aggregate interlock. But if you wanted a tighter design, they can be adjusted downward. And the other thing I'll point out is we've got this KB bond coefficient in here. That is set at, our bond dependent factor is set at 1.2 in the code for all GFRP bar types. There's some issues with how KB is determined depending upon how you figure it out. You can get very different numbers. That 1.2 was calibrated to the 0.028 inches and works well with 0.028 inches. What else do we have in this equation? We see what looks to be the service load GFRP bar stress. We've got to decide what that is. But in reality, we don't really have the bar stress there. What we've got, if you take a look, the numerator has the tensile modulus and the denominator has the bar stress. So in effect, we're dividing by strain in these equations, which brings the next question. What value should we be using for strain in the GFRP if we want to use this to control shrinkage cracking in our slabs on ground? What value do we go with? There are several different recommendations that one can look at. We want to limit that reinforcement strain, and the approach that was taken in both Code 440.11 and in the ACI 440.1 guide for FRP reinforcement is let's limit that strain to 0.0012, okay? Where did that come from? It corresponds to the strain you'd have in steel, okay, when that steel is at a service load stress of about 0.6 Fy, and typically when we're designing with steel, we'll say stress in the steel under service loads is going to be, around 0.6 to 0.67. So that's one choice. The other choice would have a much larger strain that could be used, and I wouldn't recommend that without there first being additional test results to back it up, but the strain would be expected to be in the neighborhood of 0.004 if your crack width is at 0.025 inches. And then if I get into what we've got in the guide, there we're looking at the equation they use is the subgrade drag formula, which looks something like this. And if I adjust that with a strain of 0.0012, assuming a coefficient of subgrade friction that's recommended at about 1.5, I get an expression for the area of reinforcement I want to use to control shrinkage at about, at what we see here with a coefficient of 625. If I use that 0.004 strain, that coefficient would be much smaller. So what can I do with this? Well, I think it provides for us a relationship between the area of the FRP reinforcement and joint spacing for a given slab thickness. And if we were to set that 625, that area, convert it to a reinforcement ratio, and set it equal to the temperature and shrinkage reinforcement ratio from the code for GFRP bars, it sort of implies that, gee, FRP reinforcement in amounts equal to what is specified in code 440.11 it might be possible to use them for slabs on ground with joint spacings up to 30 feet. Okay? Now that's great, right? We can space our joints further apart, we cut down on maintenance costs. But I would say that if that were to be done, that reinforcement should be chosen so that your bar spacing limits that I showed on the previous slide for crack control are not exceeded. I will note that this is all speculation at this point of my part. We need the experimental data to validate this approach, but what I'm seeing starting to come out and show up in publications, I don't think we're too far from being able to quantify an approach like that. And I'll stop at that point, and thank you.